In this video, I want to walk through how to create a simple fully connected neural network in Pytorch. There's a lot of information online and I know that it can be overwhelming, so let's go through this step by step. The outline for this video is that we're going to import all the necessary packages from Pytorch. We're going to create our fully connected neural network, a very simple one, and then we're going to do some initialization of our model, like learning rate, etc. We're going to load data. In this example, we're going to look at a very simple data set, the MNIST data set. And we're going to initialize the network that we created in this step. And also set up the loss function and the optimizer that we're going to use. Then we're going to train our network. And in the end, we want to see, well, how good is the network that we trained on the training and the test set. So to begin with, we want to import all the necessary packages. So I'm going to copy in and let's go through what each of them does. Torch is just the entire library. And then from torch.nn, we're going to import it as nn. Essentially, this is like all the neural network modules. If we're going to define our feed-forward neural network, like we're going to use the linear, like nn.linear, that's included in the nn module. If we're going to do something more advanced, like convolutional neural networks, it's also going to be in this module. Loss functions are also inside here. And torch.optim as optim, this is all the optimization algorithms like stochastic gradient descent, atom, etc. Then torch nn functional as f. Essentially, this is like all the functions that don't have any parameters. So activation functions like relu, tanh, etc. are in this one. They're also included in the nn package. So a little confusing, you could use either. We're going to use this one in this example. Then we have torch.utils.data import data loader. Essentially, the data loader gives us easier dataset management. It helps us create mini batches to train on, etc. Then torchvision.datasets as datasets. So Pytorch has a lot of standard datasets and makes it very easy for us to import them in a nice way. We're going to use this one to import the MNIST dataset. Then lastly, torchvision.transforms as transforms is like, we're not going to go into this in depth, but essentially this has transformations that we can perform on our data set. All right, so now that we have the packages and we understand like roughly what they do, let's create our fully connected network. We're going to create a class, nn, for our neural network. Then we're going to inherit from nn.module. And then we're going to create our initialization. And the first thing that we're going to do is call super nn.init. So essentially, the super calls the initialization method of the parent class, which is in this case nn.module. So we run the initialization of that method. Then we want to create a very, very small neural network. So we're going to do just 2 layers. The first one is going to do nn.linear. And yeah, so let's input some input size and then some number of classes. In our case, the input size will be 784 since the MNIST dataset has 28 by 28 images, which is 784 nodes. Then, so we're going to do nn linear for the input size. And then let's do some hidden layer nodes of 50 nodes. So very, very small. And then another one to have 50 to the number of classes. Next step is to define the forward method. So the forward will run on some input x. And then what we're going to do is that we're going to perform the layers that we created or initialized in the init method. So we're going to call self.fc1 on x, and then we want to call relu on that, the nonlinearity function. And let's call this x just for simplicity. And then we're going to call self.fc2 on x, and also call this x. And then return x. Okay. One idea is that we check if it runs and gives the correct shapes on some random generated data. So let's say that we initialize our model to be NN and 784, 10, 10 for the number of digits. And then we just initialize some x, which is going to be shape 64, 784. So essentially this is the number of examples that we are going to run simultaneously. So the number of like images, I guess. So this is our mini batch size. And then all we do is that we run the model on that input and then just print the shape. So what we want this to return is that we want to have 64 by 10. So we want to have 10 like values for each of the digits. So so what is the probability that it's like a 0, it's a 1, etc. And we want to have that for each image. So we see that it returns 64 by 10. So that we have like a rough idea that, okay, this does what it's supposed to do. Now what we want to do is we want to initialize some device. So we can either run our model on the GPU or the CPU. So what we're going to do is device is torch.device CUDA if is available. So if we have CUDA, then we want to run it on the GPU. If we don't, then we just run it on the CPU. And the hyperparameters, in this case, we're going to have an input size of 784. Input size 784. Number of classes is going to be 10. The learning rate is going to be 0.001. Batch size. And then the number of epochs that we want to train. So let's say just 1 in this case. Now what we want to do is that we want to load data. And as I said in the beginning, we can use data sets from Torch Vision. So we can just use datasets.mnist. And then what we want to do first is that we want to have some root, like where it should save the data set. Let's just create a folder called dataset. And then train equals true. This is going to be the training set. So train dataset. And then transform is transforms to tensor. That's all we're going to use the transforms for in this case. So I think when it loads the data, it's going to be NumPy arrays or something like that. And we just wanted to transform it to a tensor so that it can run in Pytorch. And then if we don't have it, we want to download it. Pytorch, if the dataset is in the folder dataset, then it's not going to download it. But if it doesn't, then we want to download it. And then we want to create a training loader. So we're going to use the data loader in this case. And we're going to use the dataset train dataset. And batch size, we're going to set to batch size, which is 64 in this case. And shuffle equals true. It's just going to, for each, when it has gone through each image in the training set and it trains it for a second epoch, and it's just going to shuffle the batches. Make sure that we don't have the exact same images in a batch every epoch. Then we want to do the same thing for, let's see, for the test set. So test dataset, test dataset, test train equals false. Now we want to, initialize the network. Our model is going to be NN of input size, input size equals input size, comma, number of classes equals number of classes. And then we're going to do this dot to and device. So this is what we talked about before, CUDA if it's possible, otherwise CPU. And then for our loss function, we're going to use nn.cross entropy loss. And optimizer is atom that we're going to use. So optin.atom. And for first, we want to call all the parameters that we have. So model.parameters. And we're going to set the learning rate to learning rate. Though we initialize in the hyperparameters. And yeah, so next step, we've imported the data, or we loaded the data. We've initialized the network. We've created the loss and optimizer. Now we want to train the network. So what we're going to do here is, first, we wanted to run for epoch in range of number of epochs. So an epoch is essentially how, one epoch means that the network has seen all the images in the data set. So then we want to go through each batch that we have in our training loader. So for data, comma, targets in train loader. One thing that is common is that we want to see which batch index that we have. So how we do that is that we take enumerate of train loader. And then here we set batch index, comma, and then in a tuple, set data, comma, targets. So the data is essentially the images. The target is the correct digit for each label, for each image. Then what we want to do is that we want to make the data that is currently a tensor to the device that we're using. So data equals data dot to device equals device. Targets equals targets dot to device equals device. Now, one thing that we want to do is that if we run this and check the shape. Yeah, okay, it's going to download first. Yeah, okay. So one thing we see here, whoa. Okay, let's restart this. Okay. Okay. So what we see here is that the number of examples, the number of images that we have is 64, which is correct. And then we have 1 for the number of channels. Essentially, this is like MNIST is black and white, so it's only going to have one input channel. If we would have colored images, this would be RGB, so this would be 3 in that case. And this is just the height and the width of each of the image. So MNIST is 28 by 28. But we want this to be just one single 784. So we want to unroll this matrix into a long vector. One way to do this is to do data equals data.reshape, and then set the first axis to be the first dimension to just remain 64, and then just do a -1. Then it's going to essentially flatten all of these ones into a single dimension. Then what we want to do, so this is get data to CUDA if possible. Yeah, this is just like reshape, get to correct shape. Then we want to do the forward part of the neural network, and then this is quite easy. We just call the model of the data. Let's call that scores. Then we want to call the loss function, which we define as criterion of scores. So this is, let's see. So criterion of, so criterion calls the input first, so the scores, and then the correct. So the input which is scores, and the target. So the ones that we have targets here. Those are the correct labels. Then we want to go backward in the network. As I said before, we don't have to actually implement like the backward propagation. So this is quite easy in Pytorch. We're just going to call loss.backward. One thing we need to remember though is that we need to do optimizer.zeroGrad. Essentially, we want to set all the gradients to 0 for each batch, so that it doesn't store the backprop calculations from previous forward props. And then in the end, we want to do a gradient descent or Adam step. And this is quite easy, optimizer.step. So here we update the weights depending on the gradients computed in loss.backward. After doing that, so that's the training. Now what we want to do, the last thing that we want to do is check like the accuracy. Let's see if it performs any good. So we created the define check accuracy, and let's input the model, the loader and the model. Then what we want to do is we want to first set the how many number of correct to be 0 and the number of samples to be 0 in the beginning. And then we want to do model.evaluate. So we want to set the model to evaluate because, well, if we would use some other techniques, then we want to let the model know that this is evaluation mode, which might impact how the calculations are done. Then we want to do with torch.nograd. So this, when we just check the accuracy, we don't have to actually compute the gradients. That would be unnecessary computation. So we just do torch.nograd to let Pytorch know that you don't have to actually compute any gradients in the calculations. So for x and y in loader, then we do first, so x equals x dot to device equals device, y equals y dot to device equals device, and then x dot equals reshape. So essentially like the same thing that we did here, right? X dot shape 0, comma -1, and then call scores model of x. And now what we want to do is that we want to take scores dot max, and we want to have the max of the second dimension. So we can either set 0 or 1 here. If we would look at the shapes of scores, this would be, as we saw previously, it will be 64 images times 10. And we want to know which one is the maximum of those 10 digits. So is it, if the maximum value would be at the first one, then it would be digit 0. So we do predictions to be scores.max of 1. So this would give us the value. We're not really interested in the value, we're interested in the index of the maximum value for the second dimension. Then we just do number correct to be the predictions that are equal to the correct label, and then we just take the sum, and number of samples will be the predictions, so predictions dot size of the first dimension. So essentially this, right, 64. And then we want to compute the accuracy to be, so I guess we could just do print, and then let's do an f string, got number correct, number of samples with accuracy. So just want to print it in a nice way. So what this does is we convert, remember these are tensors, so we want to convert them into floats. And then we don't want to print, for example, let's say we have 95 point like this. We would rather just print with 2 decimals like this. So what we can do with f strings is just like this, comma 2f. And that should be all, I think. Then we just return the model.train. So after we've checked accuracy, return the model to training. I guess it's not necessary for this example because we are done with the training part, but perhaps you would check the accuracy while you're training to see that it actually improves. Then this would be something you want to have. Then in the end, let's see, we want to run check accuracy on the train loader, comma model. And then similarly on the test set. One thing we can do also is we can check in the beginning if the loader.dataset.train, then we know that it's running on the training data. So we can do print checking accuracy on training data. And if it's not, then we can say print checking accuracy on test data. Like that. And I think this should, yeah, this should be all. So let's see if this runs. And yeah, in this case, I'm running on the CUDA because I have a GPU. If you don't, then it's going to run on the CPU. It's not really going to be any difference. So let's see, we got an error, return accuracy. Yeah, so we didn't define the accuracy. I guess we don't actually have to return it. Okay, but we see here that, so checking accuracy on training data, 93%. Yeah, all right, so training just one epoch on this small network actually gives quite okay accuracies. Well, depends on what, like 93% is okay, I guess. And in this case, it actually performs better on the test data. I think if we run this for more epochs, it's going to perform even better. And also if we make the network larger, it's definitely going to improve. But this was the idea was not to get the best accuracies, just to show an example of how we create a simple neural network in Pytorch. Yeah, so hope you enjoyed this video, and I hope to see you in the next one.